The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
The final project is a very critical part of this class. Okay, so I'll emphasize this. The assignments are simple and straightforward. If you're struggling with it, you should talk to me or Ankit or Professor Mukaigawa or Professor Oliveira, and we are here to help you. Okay, but the final project is really, really critical. Okay, the project has to be novel. It has to be something nobody has done before. Okay, or at least somebody has done it the way you are doing it. Okay, and so the problem statement has to be novel. Its execution has to be beautiful, and its impact. You should reach some results. You should show that you are solving it, or it's possible to evaluate what you have done. And we have multiple stages to get you prepared for this final project. You have to come up with at least 3 ideas for a final project. Okay, and this is very critical. If you go to the wiki on the Camera Culture group page, we have a whole section on how to come up with great ideas and how to brainstorm and so on. So I encourage you to do that. On our Stellar page, we also have a whole presentation on how to come up with new ideas. There are 6 ways of coming up with new ideas. And you should start setting up a meeting with me or any one of these people in the next week. If you're in the building, it's easy. You can just catch me. Usually between 5 p.m. to 6 p.m. is the best because there are no officially scheduled meetings. You can just come to my office and we can chat. If you're not taking this class for credit and you're a listener, I would really appreciate if you will pitch an idea for a project. Okay? And we'll have an opportunity to do that on October 30. Okay, so just come up here and say, I have this crazy idea. If somebody wants to work on this, let's team up. Okay, and then I want you to send a very simple email with, after discussing these 3 ideas, I or Ankit or our other 2 mentors will help you narrow down to maybe the top 2 ideas or maybe the top 1 idea. And then for that, you need to send these 5 things. All right. And on November 6th, we will do a 3-minute presentation. So everybody knows in the class the kind of problem you are attacking. Maybe there's some synergy between multiple projects. You can help each other find software or talk to people or get some equipment. And then final proposals are due 2 weeks before the actual final presentation. Okay, and by then you should have some initial experiments. Remember, your final assignment is due on November 13th. So you can't start thinking about your final project after the final assignment is due. You need to start thinking now. Okay. And at this stage, it doesn't have to be completely hashed out. That's why you're in the class. We'll help you think through that. And then December 4th, the class is finished. You finish really early. Because as I said, we meet on Fridays and Thursday after this. So December 10th is the last day of classes. So we are one of the first classes to finish. Unfortunately, November 27th is a Thanksgiving break. And so which means we don't have a class just before our final projects to discuss and do other things. But I will be available throughout that time, and we can help you if you need equipment, you need cameras, you need software, whatever. We can try to help you. Any questions on final projects? And Mike was saying that it might be good to know what students did last year as class projects and how they decided and so on. So Matt Hirsch is going to come and talk today about his PyDai screen, and that would be a good way to ask him how did he get started and how did it become a SIGGRAPH paper. All right, so today we're going to talk about light fields, to finish up the light fields, and then talk about cameras for HCI. So we said there are basically three ways of capturing a light field. Can somebody tell me in 2 sentences what's a light field? Inside a camera. What is it? How do you represent it mathematically? Or representation? Just a representation. That's a marker.
L of UVST.
So it's how many dimensions does it have?
Four.
It's 4-dimensional, although the world seems to be 3-dimensional. The oculus is actually 4-dimensional. And where do we get those 4 dimensions from? We have a lens. And we have a sensor. So in flat land, it's just 2-dimensional. The plane of the wall. Where are the 2 dimensions coming from? The x dimension is easy. That's 1 dimension. And the other dimension is theta. That's this dimension. Okay. So if you connect any 2 points, that indicates the direction of the ray. And so in flat land, the light field or the ray space is 2-dimensional. In the real world, in 3D, it's 4-dimensional because your sensor is going to be x and y, and your lens is going to have theta, and right. So that's the light field that we care about. And why do we care about light field so much? What is so unique about the light field?
If we capture a light field, we have captured almost, everything that we can capture.
Exactly. It's a complete representation of light that's entering the lens. So anything that you could ever imagine doing with image, changing focus, changing zoom, changing aperture size, all those things are already captured in this 4D representation. And from that you can do anything you want. And if you cannot do it using mechanically changing camera parameters, you cannot do it with light field. If you cannot do it with light field, you cannot do it by changing mechanical camera parameters. So it's a very, very powerful way of, and as we saw earlier, the light field also represents the wavefront, the phase information. Okay. So given that this is so important, photographers never talk about capturing the light, they always talk about capturing light. And that's why this is computational photography or computational camera. Because we're trying to understand this relationship. And this will allow us to build cool camera toys and also create algorithms that exploit. Okay, so given that, what are the 3 ways we can capture this? One is using the lenslet array that we saw earlier. We were just going to put. All we want to do is, right now at this pixel, a ray from here and a ray from here, they converge, and any variation in the radius along those rays is lost. And we want to make sure that we can capture this and this individually. So what are some ways we can do it? Instead of putting the sensor here, we can put the sensor a little bit back, and then put here a bunch of pimples. And the light reaches here, too bad, we can't do anything about it. But the light reaches here, and it will be mapped to different pixels. So if I have theta equals 0, theta equals plus 3, and plus 4, and theta equals minus 4, then I have captured for this given x, I have captured, let's say this is 1, 2, 3, 4, 5. Then I have captured here 3, comma 1, minus 4. And here I have captured 3, comma plus 4. Right? And so on. So I have captured the whole light field. But of course I have given up resolution. I have given up resolution because for x equals 3.5, they're just opaque film. So that light is lost. And I haven't captured. So if I had, say, here, let's say I have 1000 pixels. So let's say 900 pixels, right, on the sensor. And I'm going to chop theta into 9 zones, +4 to -4. What is the final, how many pinholes can I put here? So this total resolution is X resolution times the theta resolution. In a traditional camera, 900 is just your X resolution. But now we're going to also try to capture the theta variations in the same number of pixels. So we know that our theta resolution is 9. So X resolution is 100. So which means that our image is only going to be 100 pixels. There are going to be only 100 pinholes. And for each pinhole, I'm going to get an image under it where you have 9 pixels. Right. And from this 100 times 9 image, which is 900 pixels, I can create a light field where the space resolution is 100 and the angle resolution is 9. And what's the disadvantage? One is that you lose resolution. What's the other thing that's wrong here? You lose light, right? Because all the light that's going through this opaque area is completely lost. It's like looking through multiple pinhole cameras. It's like looking at the world through an array of holes. So most of the light is lost. In this case, let's say out of 9 pixels, 1 pixel is open, then only 1/9 of the light is being captured. The other 8/9 of the light is lost. So that's a big problem. But still, conceptually, this is very clean. Because you can say, okay, I want to capture space variation as well as angle variation. So I'm just going to chop my world into 100 pinholes and 9 angle discretized angle spaces, and I'm going to capture 9 pixels and so on. So it's a very clean, simple model. But in the real world, this is very inefficient. It's just like for a camera, we always think about a pinhole model, pinhole camera model. But in the real world, you need to use dynamics and more skills. Now,
so let me ask you this. I mean, can you really construct this in such a way that as you go to the end of your X, right? I mean, aren't you wasting part of the 9, spatial samples that you have?
You mean at the top or the bottom?
Yeah, because maybe, you can't actually have this phone opening over the entire set. Yeah, exactly.
As long as this is your sensor, and you can create a pinhole that can capture light from different directions, you're okay. There's not that big a deal. I think what you may be thinking about is that this pinhole at some angle will become really opaque. You won't be able to see through it. Is that what you're saying?
Yeah, what I'm saying is that maybe through this particular angle, the phone doesn't span the whole 9 pixels you have behind it.
Oh, that's a good point. You're leading me to the next question, which is the spacing here. What is magical about the spacing? Because if you don't have right spacing, you'll get those problems. Okay. What needs to happen in the spacing so that you actually capture all these 900 values? Yes.
The images should not overlap behind on the sensor.
Exactly. So if you think about the blob that's coming through from top to bottom, there will be some blob here. If you see the blob that's coming through here, right? These blobs are just barely touching each other. So here we have theta equals +4, 3, 0, 1, -4, and then the next one is theta equals +4 again. Right? So it's flipped, remember.
Yes.
It's going from -4 to 4, here it's going to go from -4 to 4 others. Right? Now, if I move this pinhole further or back, you're going to get some interesting artifacts. Right? Let's say I move this pinhole a little bit forward. And I'll just take one pinhole for now. And everything else is the same. Now the blob is larger. Right? If I place a pinhole at the same, I had placed the pinhole exactly 9 pixels away. If I can put it exactly 9 pixels away, the ray from the top will start interfering with it. Right? So this blob here will start interfering with this blob here. And there will be an overlap. So that's one issue. What happens if it's too close? If instead of moving further away, it gets too close, there will be a space between those blobs. Is that clear? So if it's too close, you'll get a blob here, and you'll get a blob here, and some pixels will be wasted. So this is a very important point, and this is related to the numerical aperture or the f-stop of the lens. So an f-stop of a lens, again, photographer's terminology, I don't like it, but it's easy to think about it, is the f number is simply the ratio of the diameter of the lens with the distance to the sensor. So it's the diameter, and this is your distance, OC. The relationship between the two is just C over D. So if you have and remember the diameter is in the denominator, which means that as you have a larger lens, the f number actually goes less. So let's take a concrete example. Let's say my lens has a diameter of 25 millimeters, and my focal length and this distance is about 50 millimeters. Then the f number is what? 50 divided by 20. So that's the f number. Does anybody know what's the f number after 2? In a direction camera? Like on a dial, it's usually 2.8. And then it's 4 and so on. So if you can see that if I make my diameter half, okay, so instead of 25 millimeter, I have 12.5 millimeter. Then what do I get here? I get 50 divided by 12.5, so that's 4. So the f number of a 12.5 millimeter lens with a 50 millimeter focal length is 4. Now from 2 we jump to 4. What should we do to jump from 2 to 2.8? This is where the photographic terminology gets really interesting. But maybe some of your photographers know what this means. Yes? Multiply by 1.4. Multiply by 1.4. Okay, that's also easy. But how do you, to go from 2 to 2.8, you multiply by 1.4. But how do you get 1.4? Root 2. Square root of 2. Okay. So, what is square root of 2? 1.4142. Something, right? As far as the photographers are concerned, it's 1.4. Problem there. Because we like to think about precise numbers, and this problem, and it becomes even bigger problem once you go from there. Anyway, so where are we getting the square root of 2? If you go from instead of 12, when you go from 25 to 12.5. The amount of light that's collected by this disk versus this disk is related by what factor? Factor of 4. Right? The diameter is decreasing by a factor of 2, but the area is decreasing by a factor of 4. Okay. Now, if you want, so 4 times less light coming in. On the other hand, if you want to go from 25 to some other diameter, so that you get half the light, what should you do? You should divide 25 by square root of 2, whatever that is. 18, something like that. 25 divided by 1. square root. Okay. Let's say it's 18 point something. Is that correct? 18 millimeters. I'm being imprecise here, but maybe somebody can calculate me. So when I go from here to here by square root of 2 in diameter, I get half the light. And that's what photographer mean to go down by 1 f-stop. Okay? So when you go down by 1 f-stop, are you going from 2 to 3? Or are you going from 2 to 4? What are you doing? It's such an imprecise terminology. Going down by 1 f-stop means going from 2 to 2.8. It's completely unnecessary confusion. Okay, so just get rid of this terminology altogether. Okay? And if you really want to think about the reason why it's worthwhile in thinking about the ratio of diameter to the focal length is about the amount of light. Okay? And can you tell me why that's the case? So let's say I have a 25 millimeter lens with a 50 millimeter focal length versus let's say I have a 5 millimeter lens with a 10 millimeter focal length. This system and this system have the same exact f number, which is 2. Here it's 50 by 25. Here it's 10 by 5. So both of them have the same f number. What's constant between the two? This angle here. This angle is same in both systems. And this is critical because when you're looking at the world, you want to say, at a given pixel, over what cone am I receiving light? And so that's a very important factor when you think about how many photons you want to capture. Because the angle, the cone of angle over which you're collecting the light determines how bright the pixel is. And so it really helps you to think in terms of ratios or the angles. Other than that, the rest of the terminology is very confusing. Okay, what happens after 4? What's the next f number? 5.6. What do you think 4 times square root of 2 is? It's nowhere close to 5.6. Right? It's probably whatever 1.4 times 4, so it's 4 point. Yeah. 5.64 something. Getting more and more imprecise, and as you can imagine, as you go further away, so this is the same confusion between whether a megabyte is 1000 kilobytes or 1024. Actually, it's even more confusing kilobytes. And I heard a very interesting story at Akamai when the economy was not doing so well. In the contract, they had said, we will charge you this much for each megabyte or each gigabyte. And when you're at a kilobyte, the difference is very small, right? It's less than 2%. 1000 versus 1024. But as it goes larger, to gigabyte and terabyte, the difference between the power of 10 and power of 2 is actually significant. So this woman, wakes up one day and says, you know what? We need to charge people by the bytes. The 2 to the power, not 10 to the power. And suddenly the revenue increased by 4%. And so the same kind of problem is creeping in here. That by treating square root of 2 as 1.4, it starts getting more and more confusing as you go on. And then, as you know very well, after 5.6, you start jumping. You have 8 and 11 and 22 and they're not square root of 2 anymore. You just get too much confusing. So just ignore all this. This is the most confusing thing. Going down by f-stop is actually going from 2 to 2.8. Alright. Photography school, but jargon is bad. So what we're trying to do here is our angle here, right, is decided by this ratio of diameter to focal length. And the angle here is this again a ratio of the blob to this distance. Okay? So let's call this C1, and let's call this Z, and this is L. Okay? So what we want is the ratio of Z to D to be equal to the ratio of L to your blob size. And if that is matched, then all your blobs are going to just barely touch each other. If it's not matched, then either you'll get overlap or you'll get matrices. That's the basic kind of math behind a light again. So it's great conceptually, but as we know, it's going to block most of the light. And again, pinholes have diffraction issues we haven't talked about, but has anyone done here pinhole photography? So what are the problems you face when you're doing pinhole photography?
Since there's so little light, you need
so little light, so
exposure time.
The exposure time is very long, and the image quality.
It's blurry because you could never have it infinitely small.
Exactly. So the image is blurred because of diffraction. So if you really take a pinhole, then light comes in, and it actually doesn't go in straight line. It actually bends a little bit. Because of that, a single point in the world doesn't map to a single point on the sensor, but it maps to a small blur. And this is very similar to the analogy of just using a water hose. If you have a water hose and it's open, water comes in, and you get almost the same thickness, same width of the water flow, right? But as you start shrinking this, eventually the water actually starts spraying up. Okay? When the size of your opening in the water hose becomes comparable to the molecules of water, it actually starts spraying up, and that's diffraction as well. Okay? And we have the same principle here. We have, in very simple words, we have photons coming in here with certain wavelength. What's the wavelength of green light? 500 nanometers. Remember these numbers. These are very, very, very critical. So 400 to 700 is blue, green, okay. And this is nanometers. It's 10 to the minus 9. So if the light is 500 nanometers, which is 0.5 micrometers, right? And your pinhole starts becoming about 1 millimeter, which is 1,000 micrometer. Then you're probably okay. But if you start going, millimeter and below, which is what your cell phone cameras are, fortunately, if you start getting to 500 microns, which is half a millimeter, then your wavelength is comparable to the size of your pinhole, and you start getting this diffraction artifacts. So the relationship between the size of the opening and the size of the wavelength decides the diffraction. And the formula actually is very easy. This one here is simply lambda by A. So if the aperture is A, this angle here is called beta. In radians is lambda by A. It's a very simple formula. We won't be talking about it too much in this class, in this lecture. Later on we'll talk about it. But that gives you an indication of how quickly the light is training up. So in the worst case scenario, when you have the pinhole the same size as the wavelength of light. So let's say you created a pinhole whose width is also 500 nanometer or 0.5 micrometer. What will be the output angle? It will be 1 radian. And 1 radian is how many degrees? 57 degrees. So this cone will be 57 degrees. So, it's out of the question. Even if you can can just do calculations. And even if you plug something that's 1 millimeter, so that's 1,000 micrometers, the angle is still pretty wide. That's why you need to learn. And so when camera makers are selling you lenses, really crappy lenses on a mobile phone camera, but they're giving you sensor resolution of 5 megapixels and 10 megapixels, it doesn't make sense because your image is already blurred. You don't need that many. So, if other way to think about that is, can your camera capture all this? Okay, you should just take photos later on. If your cell phone camera has a typical aperture size of say 2 millimeters, that's generous, it's usually smaller than that. And then you have your sensor, light comes in, and we're kind of zooming in into the world now, and it kind of spreads out. And let's say it spreads out over only about 20 micrometers. Okay. The pixel of a camera is about 5 micrometers. Each pixel. So if the blur is already 20 micrometer, it doesn't make sense to have a pixel that's that small. You should just have a pixel that large to capture that. So if someone's selling you a 10 megapixel camera with a 5 micron pitch, they should just give you something that's much lower resolution than that, because the numbers don't make any sense. But again, this is a typical marketing gimmick camera makers will use, where they will sell really high resolution sensor, although clearly you cannot really capture that big that good resolution. Is this clear? So, and there's a new trend. I think camera makers have started selling in terms of megapixel rays, and now they have to start selling cameras with low resolution. I think the latest Canon has lower resolution than its previous version. I believe the G6, I think it's 12 megapixel, and what they release now is only 10 megapixels. Because they realize it doesn't make sense to just keep boosting the megapixels when the aperture and the lens is not changing that much. So recently I was working on a project where they want to capture 50 gigapixel. 50 gigapixels, 50 times 10 to the 9. This is usually 2 times 10 to the 6 pixels. And as the megapixels increase, the size of the, as you can see this ratio here, right? As the megapixels increase, the size of the lens required increases correspondingly. Okay, and that's why expensive cameras have much bigger lenses, much wider. Yeah.
Question. If it's so clear, wouldn't it be much more helpful to come up with a measure that you took the stars, the size of the camera, like let's say 10 megapixels, and add the amount of pixels that you can really get to capture.
Exactly.
And actually,
and the camera maker should just announce that.
Yes, I mean, of course, it's a marketing thing.
Yeah, I know.
But for scientific purposes, isn't that a good?
Yes, there is. So there are all these measures called modulation transfer function and space bandwidth product and so on. And if you want, we can discuss about that later on. It's not so central to what we're doing here. But when people talk about, yes, let's get more resolution or let's do super resolution, those are the laws of physics. If you have a water hose, or you're going to put something really a tiny aperture, the water is going to spread. It's not going to create a very tiny spot. So the other way to think about this is, how can you create a water pipe that creates a spot that's really, really tiny? It's only 1 millimeter. You cannot do it. You start decreasing your ball size, water that you spread out eventually. So, and it's almost, it's funny how nature works. There are always all these limits as you get closer to certain thresholds. Right? I mean, if you think about the density of water, it decreases as you decrease the temperature, but at some point the density actually starts decreasing again. Same thing with diffraction or water. There are a lot of this phenomena where it seems like nature automatically puts some stuff of how small or how large things can get. So we're talking about resolution, we're talking about the ratio of the diameter to the focal length. There's a very minor and very subtle point here. I'll just make it for those of you who are thinking about the effective focal length, effective F number versus F number, which is, although we're defining it by diameter to the focal length, the sensor is never exactly at the focal length, right? Because that will be the case when you're looking at infinity. When you're looking at somewhere closer, the sensor is, so if the focal length is 50 millimeter, the sensor is 50 plus, like 51 or 52 millimeters. But that's small enough that you can ignore this calculation for other times. But the true way to calculate that is by taking into consideration that small shape. Okay, so we were talking about pinhole, then we started talking about how pinholes are not great because they lose light, the exposure times are too long, and the image is blurred. Right? And all those problems are going to appear here as well. It's just that what we have created here is an array of 100 virtual cameras. Okay? These are 100 virtual cameras where each camera has a pixel, a resolution of 9 pixels. So we have converted one big camera into 100 cameras, each with 10 pixels. And in the real world, it will be 10,000 cameras, 100 by 100, each with a resolution of 9 by 9 pixels. That's what makes it interesting. Right? From one camera, now we have created 100,000 cameras. And as we saw last time, you can do it at home, just by printing it. Alright, so just like in regular cameras, we don't use pinholes, we use lenses. We want to replace each of these pinhole now with lenses. Right? And that's why we call it a lenslet array. So I'm just going to draw on top of this with a different color. So if it gets too complicated. Okay? I'm just going to draw a lens here. Right? And it's going to do almost the same task. We know that at the center of a lens, you can just shoot the rays and they just go straight. Right? Because remember, a lens is made up of sets of prisms. And the middle one is just a sheet of glass. So when it goes to the center, nothing changes. It's easy to remember that. When you use the lenslet, we can do the same thing. But there is one very special two actually very special constraints we had to achieve to make this happen. Because it's a lens, and we're trying to form an image. When we're building a electric camera, what we're doing really is forming an image of the lens on the sensor. You remember we had this concept of a conjugate plane, a point in 3D and its corresponding location on the sensor position is for conjugates of each other. They correspond to each other. And here what we want to do is create a lens which forms an image of the lens on the sensor. So I have to choose its focal length and its distances in such a way that if I put a point here, I get a sharp image of that point here. Because these are our 9 theta's. And each theta here has to map to one exact pixel. So that makes it extremely difficult because now we're almost in a microscopic world. I have to create these lenses extremely high quality so that an image of a point kept at about 50 millimeters is formed at some really small distance, usually well below 1 millimeter. It's about 500 microns. So this becomes very challenging. This is a very specific constraint. There's exactly one plane in which I can put this sensor. If I put it too far here, then the image of the lens of the sensor will be blurred. If I put it too close, again the image will be blurred. Okay. And that very special constraint makes building a light field camera out of lens slats extremely challenging and very expensive. Creating this resolution. So let's say by the way, all these things we talked about, where if you put the lens light, you can put the lens a little bit further out, right, and change its focal length so that this one is still imaged here. But conceptually, it's still a pinhole. So if you put the lens light over here, and the ratios of this to this is not matched to this to this, then you will get overlap. And if you put it too close and change the focal length correspondingly, you will get dark spots everywhere. So we still have to worry about Steinmetz emissions. So there's an additional thing you have to do, which a lot of people forget, which is if there's some point there's some point here out in the world, which we call x again, this is x again, right? And what we're trying to do is this point is in focus over here, and then we're going to chop this into 9 rays, 9 ray bundles, theta equals +4, theta equals -4, and the one that goes to the center is theta equals 0 +1. That is right in focus. And what we have done is we have captured the light field of this particular object. If I want to create a light field at a slightly different plane over here, question is, can we, once you have completed, remember we made this claim that if I capture this 4D light field, I can do anything I want. I can focus here, I can focus there, I can reduce the light, I can change the aperture size, I can change the focal length, I can do anything I want if I capture that particular light field. So one question you'll be kind of thinking about when you are doing this assignment is, given that you have captured a light field at one particular plane, how do you recreate it at a different plane? Either by refocusing it or some other things. What's the difference between this situation and the assignment that you're doing? Because you're using array of cameras. And we last time realized that the lens is what? It's an array of pinholes with prisms. I can chop the lens as, come over here. You can think of a lens, you can chop it up, and you can treat it the same as these pinholes, right? With corresponding prism next to it. In this case, just a sheet of glass. It's a pinhole plus a prism. When you take a picture with a camera array, unfortunately you don't have this prism to do that computation. All you have is a set of cameras. Thanks. All you have is a set of cameras. You don't have this prism. And mathematically, you're going to shift the image, which is equivalent to putting the prism. So you're going to take top images and you're going to shift them by +2 pixels, +1 pixel, 0 pixel, -1 pixel, -2 pixel. And that's the same as putting a set of prisms. Is this analogy clear? Alright. So, once we have done all these two classic ways of thinking about capturing light field, again, 1908 is when this idea started coming up, more than 100 years ago. But the practical solutions came much later. Remember, back then it was about film, quite challenging. We want a third solution that came out just 2 years ago of capturing light field. Okay. We're going to look at that for the next few minutes and then switch over to anybody has thoughts on some other ways of capturing the light field? Maybe fourth way. Yes?
I think this is a paper last year, but we have a LCD and you just multiplex.
Excellent, excellent. So, you can come up with lots of hacks to kind of go around this. So one very interesting hack these guys came up with was they said, I don't want to put anything close to the sensor. I'll just take a traditional camera and let me erase some part of it. I'm going to erase this part up here. Because all I care about is at this pixel, I want to know how each of these rays behave, what is the radius of each of these rays. So all I will do is I will block this part of the lens and take a full photo. Okay? And that will give me this direction for each pixel. Okay? Then I'll take a second photo where I will block everything except this region. Take a photo. And if I take 9 such photos, then instead of getting 100 times 9, what will I get? You do 9 pictures. Each has a resolution of 900 pixels. So you'll get 900 times 9. This is over time. And this is a single x pixels. This is x and 9 times x. So this is what the setup paper was about. And they came up with better methods to mix it, but that was the basic concept. Okay, but this is really it's not a new method because it's using the same basic concept that the block is. So the pinhole versus lens thread is a different solution. Yes, something of your own. Yeah, okay. What else? Think about all the work, in that document or in that presentation about how to come up with new ideas. One way to think about all the hammers you have, all the knobs you have. On a camera, you have a knob of exposure time, focus, focal length, moving the camera, wavelength. Think about all the ways you can use those parameters to reach the scope. So this is called in that X to next is called X down. And you know what it is.
Well, it's like so we see now that the image capture is playing. So we use that instead.
Why does it have to be a plane?
Yeah.
It could be something else. Exactly. What should it be?
Okay. Then what we have. If you have a sphere.
Like on some kind of a concave or convex sphere. That's a good start thinking about it. Remember, CAT scan machine works on almost the same principle. We saw it last time. In a CAT scan machine, it is like the sensor is on a cylindrical surface. Or if you're thinking of doing some, non-interfering optical communication, Sam is interested in this. You would do the same thing. Now, lots of signals are coming from different directions. I want to demultiplex them and recover them with artificials. You will put an array of antennas. How about creating a Lightfields antenna? That would be a good project. In simulation. Okay. So let's think about this third solution, which is a relatively simple idea to explain actually. What we're going to do is not use lens thread array, but use a pinhole array. Okay. I'll show you how this works, and then I'll explain why it works. All we're going to do is place a mask. Instead of a pinhole array, we're going to place a mask that has certain transparencies. So here instead of pinhole array, we're going to be basically if I plot its transparency, it's going to have some strange pattern. We print this film and put it instead of a pinhole array. And if you do that, it turns out you'll get a picture that looks like this, if you look at the parts that are out of focus, you'll have this really strange encoding. For parts that are out of focus, it looks like the light has been attenuated a little bit. But, they're the same. I think it's slightly better here than over there. See it. But for out of focus, this is really strange effects. Okay? And I'll summarize how it's computed and then come back and explain why it works. And all we're going to do is take if you take a traditional camera and take a 2D photo, if you take any image in general, and just take its Fourier transform, which is what JPEG compression will do as a very first step, you realize that most of the energy in this Fourier transform is in the low frequencies. In 2D, you put low frequencies in the center. In 1D, you put the low frequencies at the left edge. So most of the energy is in low frequencies, low spatial frequencies. So in the center, you have the DC component, which is the average of all pixels, and then you have first frequency, which is how many sinusoids you can put in this image, and so on. Okay. Most of the energy is over here. If you place this very high frequency mask where the pinhole layer was, and then take this 2D Fourier transform, it looks really, really strange. It has a lot of energy in high frequencies as well. And those of you who are used to looking at oscilloscope or radio frequencies and so on, if you just capture the radio waves, all the radio stations, and look at the spectrum, it will also look something like this. You will have some carriers in the middle, and there will be a band around the carrier, and there will be a guard band. Right? So 99 megahertz station is transmitting some audio for about 20 kilohertz around it. 100 megahertz stations transmitting audio 20 kilohertz around it, and so on. So this is how the spectrum will look like. Just capture any telecommunications signal. And something similar is happening here. And I'll come back to this and explain how this exactly works now. Okay. So that. And what we're going to do eventually is take the 2D Fourier transform, which looks like this, and we're going to shift it. We're going to take this 2D world and make it into a 4D world, a 4D hypercube. And we're simply going to take this inverse Fourier transform and recover all those images that you would have captured if you place the camera at different positions. It's as if we have taken the lens and split it into 81 different cameras, 9x9. And as you can imagine, from this 81 cameras, now we have captured. So for every one of those slices on the lens, we have captured an image that's only 200 pixels per 200 pixels. But we have created 81 such pictures. And so here, you're just seeing some of those 81 pictures. Few of those 81 pictures. But using this 81 camera array, the box I showed you last time was a 5x5 camera array. And you can think of this as an 81 camera array. But we didn't have to build a new device. It's just an ordinary SLR camera, medium format, and we just placed this mask. That's it. And suddenly we have, for $2 extra, we have now 81 cameras. But of course, each of them is really resolution.
What's the advantage of this mask to a pinhole, or a pinhole mask?
So the question is, what's the benefit of this type of mask over a pinhole array? What's the answer? What are the disadvantages of pinhole arrays?
More light because it's continuous.
Right. So it's more light because the almost 50% of the light will go through. Okay. So previously it was a pinhole array, so very little light was going through. What's the second problem? Yeah.
Which you get from the pinhole way is not established, but with this you have to reconstruct or
Exactly. If you have a pinhole array, you have a lot of diffraction artifacts. Even here you'll have some diffraction artifacts, but they won't be as severe.
So it's basically simulation, that's the lens-led array.
Exactly. But after computation, what you capture looks like almost an ordinary image, except those very strange effects at out of focus.
So, but you're saying you're applying the inverse transform to the small sessions of this spectrum, right?
No, not really. Not really. We're going to take this full 2D image, and we're going to tile it and create a 4D hypercube. So let's make it simple. Let's say the image was only 1D, just this horizontal line here.
Right.
Okay. If you take this frequency transform, actually I have a slide for that. Okay. If you take the frequency transform, you will capture. There will be some 1D frequency transform that looks like this. Okay. And what we're going to do is, so let's go step by step. So in the frequency domain, this will be a little bit of a stepping ahead. We'll come back and talk about coding techniques in a couple of lectures, and this will become more clear at that time. But basically, we have some variation in x and some variation in theta. Right? We saw there. In this case, it was 100 by 9. In this case, it's 200 by 9. That's 200 by 9 actually. 200 by 9. We're just thinking in 1D now. And then our sensor, however, is just 1D in this case. So although we want to capture 200 here and 9 here, we cannot capture them on this 1D sensor. So what we basically do is take that 1D sensor. We're going to take that 1D sensor, and it's going to capture different parts of this signal. And then we're going to reshape it. We're going to chop this part and put it here. Chop this part, put it here. This one stays the same place. Take this part, put it over here, and take this part, put it over here. And now from a 1D signal, we have created a 2D light field. Okay. And it may not be immediately clear, as I said, because we haven't looked at coding scheme. And from that, we can recover.
All right. So you have all the coefficients for the entire image.
Exactly. The whole calibration for that entire image. Yes.
What about aliasing?
Sorry?
Aliasing.
Frequency domain aliasing?
Yes.
So, okay, we'll talk about that. If you think about this particular problem where we had an overlap or undershoot, that's also a type of aliasing. Right? Because we're trying to capture more signal, but we don't have enough bandwidth here. And it's the same exact problem here as well. So you have to assume that the scene doesn't have, very high special frequencies, otherwise they will alias and mask better as low frequencies.
But does it mean that you do sample the original image in much lower frequency?
You can only, so you hope to recover only 200 pixels in the world.
Here, if the spectrum is it's very centered.
Right.
You could sample much
Yeah,
lower.
you have to hope that your spectrum looks something like this.
Yes.
If your spectrum actually had a lot of energy up here and down there, then yes, you'll get a lot of aliasing.
No, I mean that you can sample this signal in much lower frequency than it's actually sampled. Right?
Repeat that.
You can sample it in much lower frequency than actually you see the sample.
Using what? Using compressive
You use
sensing?
no, just sample it in low frequency.
Just take this.
Sample. Yes.
Yeah, I mean that's exactly what happens in JPEG, right? You take whatever 4 megapixel image,
Yes.
and then you're able to represent it as half a megapixel image. Yes. Because you're able to take only the lower frequencies, lower special frequencies, and represent them well. And you take the higher frequencies, but you don't represent them that well. That's how JPEG or traditional frequency domain compression works.
So you assume.
But we cannot do that in the real. We cannot do that in optics.
Yes.
You can do it in software. So here is a method to do that, not the compression, but the remapping in optics.
So you assume the signal is oversampled.
Yeah, exactly. So if the world actually had a checkerboard, extremely high resolution checkerboard, then you'll have problems. It's a similar effect. If somebody is wearing really fine structure and you take the picture, you see this aliasing artifacts. Or if you take a fence, very high resolution, take a picture, you get this strange effects. So it's the same problem here. It's just sampling theory. You cannot get around aliasing that easily unless you do some pre-filtering. I won't go into the detail.
So Ramesh, do you have to apply this to each channel separately?
You have to do it for every color channel. That's right. And from that you have captured it. So let's look at the intuition of how exactly this works. And there's a frequency domain explanation that many of you have seen. And I'm going to give you a very simple, intuitive reasoning of physics. Okay. So let's come to this problem of replacing a pinhole with this new type of mass, which we call heterodynamic mass. So here we had a pinhole, and I'll just draw it again. A pinhole, and we had 9 values coming in. Theta equals minus 4, theta equals 4, 4, minus 4. Okay. And then we took the next gap over, right? And this was doing the same thing again. Over there. 4, minus 4, and so on. And by using this trick, we're not going to get more solution. We still have to miss some information in the middle. It's just that we don't use the light. We just use those special frequencies. So, small digression, and we're going to talk about something called Hadamard multiplexing. The problem is very easy to explain in this particular. Let's say I give you there are several bags with different weight. Okay. Weight 1 to weight 9. Okay. And I tell you to weigh them, and at the end I want a solution of what the weight of each of the bags. Simplest method is you take the weighing scale, put each of the bags one at a time, and you have a solution. What are some other ways you can do it? If you don't want to do one at a time, what do you do? Sorry? Do all of them, but that doesn't give you, you cannot decompose it into 9. You must make 9 measurements. I'll give you that answer. You must make 9 measurements. One choice is you just put one bag at a time. And you have 9 values, one of them is. But let's say your scale actually, so let's say the weight is from 0 to 100. Okay. Sorry, the weight itself is 0 to 10. But let's say your scale doesn't work very well in the first couple of hops, first couple of pages. Statement. Okay, so the scale works pretty well when it's in the linear phase. Okay, but it doesn't work so well when the weight is too low or weight is too high. So what you want to do is stay in the linear range from the beginning. And cameras work the same way, that's why I'm doing this. If the light is too low, if the light is too high, the camera cannot figure out the exact intensity. But if the light is if the value is going from 0 to 55, then when you pick it 50 to 200, the camera works nice in a straight line response. But if it's too dark or too bright, the camera cannot handle it. That's all. And the similar analogy we will do. So one solution is to do one at a time. The other solution is I can put a group of them. Okay. Let's start with a really simple example of 3. Let's say I have 3 of them. I can put one at a time, or I can put 2 at a time. First I can do W1 plus W2, then I will do W2 plus W3, and I will do W1 plus W3. Okay. If I take these 3 measurements, from the 3 measurements I can figure out what each of those ones are. Okay. And you can actually write this down as a very simple linear system. I will say that as well. Okay. So let's say when I put the first 2, my measurement is M1, M2, and this is M3. And all we have done here is we have said I made 3 measurements, M1, M2, M3. What I would like to know actually is the weights, W1, W2, W3. Okay. But the way I have measured it is the first one is W1 plus W2 and not W3. Second one is W2 and W3 but not W1. And okay. That's our linear system. A equals B. and we just call it in the system, and we can tell you from those three measurements what the original measurements were. As simple as that. And it's very simple. It's 110. It's not even half or more. Purely analytical. So for 3, this seems like a very good solution because now we are staying somewhere in the middle range. We are not at the bottom range of this weight, and we are. If you put all 3 of them together at the same time, you might go, very far over here as well. We're staying mostly in the middle range here because we're taking the sum of the 2 weights of this. So this is very convenient. And Hadamard multiplexing is basically the same concept. Instead of taking 3, now if I have 9 or n such measurements, I'm going to basically take about half of them randomly. And I'll take about half of the bags, put them together, make a measurement. Then I'll put them apart. Again, take some other half and do some measurements and so on. So if I have 9 of these, I will create a matrix that looks something like this. I will have I want to measure 9 weights, but we want to go to 9. My measurements are N1 through N9. Okay. And what will we have here? What's the size of this? Sorry? 9 by 9. Right. And just like we put down the numbers here, we're going to put some random numbers. So instead of putting all the bags, that would be equivalent to putting all the ones. Or, okay, let's step back. If I just put one bag at a time, what will this matrix look like? So let's go back here. Okay. It will be just 1, 1, 1. And that's what will be 0. Okay? As simple as that. And the same thing would be here along the diagram. But if I do this Hadamard multiplexing, out of the 9, I will have roughly 4 or 5 bags placed together. So I'll put randomly 1, 0, 1, 1, 0, 5, 7, 8, 9. Right? So I'll put, 0, 1, 0, 0. That's one sequence. And then I'll take the next one. 0, 1, whatever sequences. I'll have 9 such random sequences. We have about 4 or 5 are ones now. And this is how Hadamard multiplexing works. As simple as that. So instead of taking one measurement at a time, we're going to take a linear combination. In this case, just a sum of about half the quantities. And the benefit of that is that you're staying in a range that you're comfortable with. I've used the analogy of this one with where we're going. Using a pinhole is like doing one measurement at a time. You're only measuring one ray at a time. Using a lens sled is like putting all the bags at the same time. And what we're going to do now is place a mask wherein only about half the values are going to go through, half the range are going to go through. Okay, so if you're putting only half the input variables and measure it out. You see the analogy where this is going? Can everybody predict what the pattern will be? Okay, so let's focus on this one slab here. We just focus on one slab here. Light comes in, 2 and 3. Instead of 9, we just take 3. Instead of just blocking this light here and here, okay, what I will do is I'll block it from certain directions. So let's say I will make this, actually for 3 it doesn't look as interesting. So let's go to 5. I'll make it 1, 1, 1, 0, 1, 0, 0. Okay, so 2 out of 1, which is about half. What's going to happen is for certain part of the image, if you look at the pixel here, I shoot this is my lens, this is my pixel. If I shoot a ray here, it's blocked. But if I shoot a ray here, it goes through. And if I shoot a ray here, it's again blocked. Okay. So what I'm getting at this pixel is not sum of all the rays, but some limited combination of phase. If I go to the next one, I get some other combination, because for this one was blocked, but for this one, this goes through. Essentially. But now this one is blocked. And so on. Because of this displacement, the combination that you're getting is actually shifted. Right? And once you have done this linear combination, which is what we have here, about half the light goes through. But what we have received here is the linear combination. We have this measurement, so we don't have the original ray intensities. But by simply calculating it, we'll recover these intensities and we're ready to go. We're back to a traditional spectrum again. That's a very easy way very intuitive way of thinking about how we can use Hadamard multiplexing with a light field. Again, this motion. So we get half the light, still lose half the light, but this glass half empty or half full. In this case, we at least have half full glass. And it's very easy to create. Just $2, you put the mask in, and the light can always ready to go. Fortunately, you have to do a lot of computation on this inversion for the whole image. If your image is 16 megapixel, this matrix could be 16 million times 16 million if you do it in a brute force fashion. But of course, you use smarter methods like this domain techniques to do this inversion using spectral methods or some other Fourier projection based methods that make it very important. So we won't go into the inversion, but we're going to state the problem as A equals B and say that it's possible to do it for X. Yes?
You must get Hadamard or is something sorry
That's a very good question. So what I showed you, I kind of cheated here, right? I showed you a mask that looks like cosine. And what we recently realized, just in the last 1 year, is that Hadamard and cosine is one and the same thing. So if you take a bunch of cosines, and it's a frequency domain projection, by the way. So that's why we have it here. So if you take cosines of different frequency, so this is like taking the DCT, right? When you compress an image, you take projection from different frequencies. What we're doing is we are projecting on again different carriers and so on, right? So if we do I give samples for example. If I do cosines, right, and then I'm going to make them sharper. Right. If I place all of them together, you start getting that pattern. In the center, you get a bright spot, and away from it, you get a dark spot. And the sum of all this, as you can imagine, ends up being something like we repeat, and then some variation, and then we repeat, some variation. So that's the pattern you're seeing. And it turns out we can place these cosines in such a way so that you actually get a binary term. And Matt will very briefly talk about it, of how you can actually create a binary term and achieve the same exact verification. And so something that we studied before, and we realized it's a very minor contribution, but it's very useful because printing a binary mask, as you can imagine, is more convenient than printing a mask where the opacity is changing.
And when you phrase it as a linear system, there's no sense in having, blocking half of the light or so. I mean, partially with partial transparency, you could just go binary anyway.
Yeah, exactly. If you go binary, it's easy to express, but you're still going to lose half the light.
Yeah.
Zeros are going to block out all this.
Yeah, but I'm saying instead of using say 0.75 or so, I mean, it's still a system.
That's a great point. So let me rephrase what Professor Rodriguez is saying. He's saying instead of ones and zeros, which means the sum of all this is still half of the total light, why not make this 1 and 0.75 and 1, 0.75? So you still have this variation, but most of the light is going through. And this is actually a great topic for research as to what exactly these patterns should be. And for us, binary was very convenient from 0. And if you actually play with that parameter space, you get many different interesting solutions. Some of them are geared more towards taking a 2D photo, and some of them are geared more towards capturing a light field. So, for example, if this is all ones, then you just got the ordinary photo. If this is all ones, that means every point is transparent, which means there is no mask basically. If you put all zeros, that means it's a completely black field, nothing goes through. If you use this pattern, then it's a random pattern. But if you use any values in between, then again you're optimizing the model. Yes?
I guess if you create any linear equations like where the number of linear equation is equal to the original data only you can implement it. But I thought that the reason I use the Fourier is that it's the aliasing problem. It's like you decode in the Fourier in the Fourier domain, and you decode it is fairly easy. And it's very easy to figure out what kind of filters you want to put in front of your image to prevent everything.
Right, exactly.
And I wonder whether you get similar effect of what.
So ideally, you would like to do a lot of this processing purely in the optical domain, but we don't have a pressure. The light is traveling at the speed of light, and we can only do blocking and unblocking. So if you had a way to kind of sense the image first, and once you have sensed the image, then change your mask so that you can choose the right parameters for the scene, then what you're saying is true. So in case of like software compression, you get to look at the signal before you compress.
So by once you pick it up and not any, it's not just based on the image. I mean, the image might have any high level, high frequencies.
Right.
But you know that you have some number of sensors and you cannot capture frequencies higher than.
So pre-filtering.
Exactly, and it doesn't matter where the scene is, but to prevent anything,
right.
You can put the filter that matches your camera.
Exactly. So what Dina is basically asking is, if I know that my scene, instead of having 200 pixels and 9 variations, so let's say I put a hologram. Okay. What I'm going to do is put a hologram here and then capture its light for you. And I'm going to assume that the hologram has exactly 200 pixels and I have 9 views for each of those pixels. Right. Then what I have done is built the correct system. But let's say somebody gave me a hologram which has actually 400 pixels and let's say byte number is 300 pixels and then only 6 views. Right? I don't know a priori what you placed out there is a 200 pixel hologram or a 300 pixel hologram. I will continue to decode that as a 200 pixel hologram. But the problem will be, because the scene has higher frequencies, it will alias the same question you're asking. And you have no idea of knowing it of priority. So a typical solution in any signal processing, any device that is doing sampling, is you pre-filter. You reduce the frequency by smoothing it or cutting off higher frequencies so that it will not again masquerade as low frequencies. In the optical domain, unfortunately, it's very difficult to create a diffuser that will convert something that's 300 pixels to 200 pixels purely in optics. You can do it in software. You can smooth and filter in software, but it's not that easy to do in using software. At least we don't have a solution. Maybe you will come up with a solution. Once you do that, then you can handle all this. Yeah.
So it seems from the figure that you are modulating with a variety of carrier frequencies.
Right.
And so I'm a bit confused about what's happening to, like typically when you modulate you have it's a complex number and you have the phase and the magnitude.
Right.
Are you capturing both?
Only magnitude. So the other way to think about that is, as I was drawing this cosines, instead of 1, 0 and all this thing, what we're doing is we're doing Fourier projection. So very first frequency we have is, first cosine. Here. The second one we have is a higher frequency cosine. The third one is an even higher frequency cosine. And we have this 9 cosines with 4 with plus 90 phase and other 4 with minus 90 phase. And the middle one is just BC. Okay? That's exactly what we're doing for this particular pattern. And it turns out instead of using cosines, we can also do a combined effect. That's a little bit of the
Are you doing something because now are all these Fourier transforms different, or some of them are going to be just symmetric?
No, they're going to be completely different. They're going to be all completely different.
So
because remember, I'm taking cosine and it's phase shifted. 90 degree phase shifted. So basically, again, I have 9 unknowns and 9 measurements. And I can come up with any mixing matrix as known. I can make them bunch of ones and zeros, which is the one multiplexing, or I can do a DC or some kind of a Fourier projection, or I can do Weyerhaeuser projection, anything.
From the way you described putting the mask there,
right.
The way this matrix is formed, it seems like the second row is probably a shift of the first row.
It could be if it's on the one multiplexing.
Okay, so there the inversion probably can be easier because you know the pattern of the matrix and it's not a brute force inversion. Maybe you can do elimination.
Exactly. So all the beauty and elegance of the effort comes in choosing the right type of mask and using co-designing a decoding scheme that's doesn't amplify your noise and so on.
I was going to just prefer, yes, maybe use some kind of high frequency cutoff already.
That's the same question that Dina is asking. If you can cut off anything beyond 200 so that the from 201 to 300 doesn't come into the picture. I like to think in the discrete domain because I want to do this domain. That's why I get the continuous domain. Because
I just did this from a little while back. Can't we do something with considering the layers of data instead of arrays getting past them?
So it turns out very cool. Whether you think of them as 4D ray space or you think of light as waveforms, this one's for all measure the same.
Yeah, I'm just thinking back to the guy who was doing this CCD.
Oskan from UCLA.
That's below diffraction.
Right, but he's using diffraction for that. And we'll come back and talk about this when we talk about sampling. So, a lot of you are wondering, okay, where does it all fit in? This seems like a lot of math, a lot of linear algebra, or something you can just put a pinhole and be done with it, or let's say that. So, we have a good example right here. Matt will explain to you how the same exact technique can be manipulated in very interesting ways to build an NCI.
Yeah. So, just a quick question before that. So have you already compared the results using this cosine mask with the binary ones?
Yes. So in fact, he will show you.
Yeah, because in theory, they should be equivalent, but in practice, because maybe some high frequencies that you introduce by the binary mask,
right.
And then you have to truncate at some point.
In simulation, they're identical.
Yeah.
But you're right, because what ends up happening is when you print these cosine masks, your intensities are actually not very smoothly varying like a cosine, but it's actually varying like some kind of a step function, right? And so on, because just digital levels when you print these things. So that ends up creating a lot of problems.
Yeah, and for the binary one as well, because then you're going to have some sharp transitions that in the Fourier domain they may go all the way.
If your positioning of the sharp transition is not right and your model is incorrect, again you need to flip that. So the calibration is very key. But the one benefit is that because now we're using masks rather than lenslet, you don't have to have the lenslet so that the image of the lens is created as a sharply focused version on the sensor. And remember, we have this very, very strong constraint that we must put this lenslet array so that the image of the lens is formed on the sensor. We don't have that anymore. Even if we have some slop, some tolerance in where exactly where to put the mask. Because all we're doing is we're taking the values we want to measure, we're going to mix them around and get new measurements and just try to report it. That gives us a lot of freedom. So if you go back to the example, to the analogy of 9 bags, instead of doing a very specific combination of those 9 bags, if I did a slightly different combination of the 9 bags, my mixing matrix may not be most efficient, but it will be good enough to do a reasonable job of it. Okay? So that gives you a lot of flexibility in building this. So Matt is going to show you how we can use this heterodyne technique.
So Ramesh, but it seems that the binary mask may introduce some diffraction artifact.
They do. Are you going to talk about that?
I
I'm not sure I got to that.
Okay, that's fine.
You can see the results and then we can talk about it.
Yeah, and just you can just go slow because we just talked about it. So it's a bit.
Okay, yeah. So.